Good afternoon, everyone. Thank you for being here. My name is Ivan Chertov, and this is my colleague Emma Lebars. Today, we're excited to present a project, Demand Forecasting and Inventory Management for H&M. We have taken a data-driven approach to optimize warehouse space and stocking. Let's dive in. So before we dive into the details, let me guide you through the structure of the presentation. We will begin with an overview of the business context and the objectives of our Capstone project. Next, we'll explore the data we worked with and the insights we derived during the exploratory analysis. We will then get to the flesh of our project, the prediction model we used, and of course, share our results with you. After that, we'll introduce our inventory rebalancing strategy and also have some key insights. So, to set the stage, let's talk about the business context and objectives of our project. A primary objective is to provide accurate demand forecast for H&M. This will help optimize inventory space and ensure better stock management. But now, why is this important? Effective stock management prevents overstocking and shortages. By aligning inventory levels with actual customer demand, H&M can improve sales performance while simultaneously reducing storage costs. A primary goal for this project is to develop a forecasting model that identifies high-demand products, especially during peak seasons. This model also supports a strategic inventory rebalancing process. This is the foundation of our work. Next, we'll explore the data. So let's go. The dataset includes transaction data from H&M online sales. It spans from September 2018 to September 2020 and is publicly available on Kaggle. We have a big data set with over 30 million transactions and 104 articles, and we focus on following key attributes of the data set, which are product type, color weekly sales, average price, and customer counts. But let's have a look at the data itself. And at this point, I give the floor to my valued colleague, Emma.
Thanks, Ivan, and hello, everyone. So first, we decided to take a look at how many units were sold over time and look at the fluctuation of the monthly sales. First highlight we inferred was a significant peak around the summertime period in 2019 and in 2020. And we see a bit of a decline in the number of units sold during the winter month, so around December, January, February season. Then we took a look at the best-selling category of items. As we can see, dress, sweaters, and trousers are the most sold category, and they consistently dominate the amount of units sold. So this item accounts for the largest share of units sold, making them a key focus for inventory planning and demand forecasting. Then we also wanted to look a little bit at the colors of those items. And as we can see, trousers, dresses, sweater dominate the categories, of course. But in terms of color distribution, black is one of the most sold color, especially for the trousers categories. And then we saw also blue and white being some of the most sold colors in terms of units. Here we decided to take a look at the seasonality aspect of the units sold. So as we can see, trousers are pretty consistently sold throughout the year, while dresses and sweaters have a seasonal pattern. Dresses are mainly sold during the spring and summertime, while sweaters are sold during the fall and winter time. This seasonality is crucial for inventory planning. By understanding the patterns, we can better align stock levels with seasonal demand and reduce overstocking and shortages. Now we're going to have a look at our prediction models, and I give the floor back to Ivan.
Thanks, Emma. Now let's take a look at how we build our prediction model. To achieve reliable forecasts, we turned to machine learning and dove into exploring various approaches. So basically, we started with random forest. It's a very famous machine learning algorithm, which was too inaccurate for us. Then we tried another algorithm, and by the end, we came up that we maybe can combine them. And our first approach of an ensemble model was a combination of random forest and XGBoost and PyTorch. And it was simply too CPU heavy. And at the end of the day, we came up with our final ensemble model containing of random forest regressor, linear regression, which you also probably know from your bootcamp, and MLP regressor, which is also a neural network, which worked well with our computers. And at the end of the day, we used Ensemble Forest as a meta model. And what a meta model does is basically combining predictions from the base models. It learns to weight them based on performance and delivers more accurate final predictions. And now Emma will tell you more about training of the model.
Thank you, Ivan. So this is how we decided to split the data. So we took the training set that starts of September 2018 all of the way to the 1st of January 2020. Validation set was the month of January 2020. Test set was February 2020. And then we asked a model to make 4 weeks worth of forecasting, like telling us how many units will be sold and like which category and which color. So we make the decision to exclude all of the COVID period, so everything that comes after February 2020, mainly for reasons that COVID was an odd time in our lives, and we had all different behaviors, and we just also hoping that would have been like a one-time event. And so we thought that it would be better for the training or long term of the model to exclude this time period. So here are the model of the training, the result of the training model for the month of February 2020. Our model predicted 881,000 units sold, while the actual sales were 875,000. Overall, we are slightly bit over-predicting by 0.68%, but we feel like this is a very strong model that had very good predicting capability and made a pretty almost exact prediction of how many units will be sold in February 2020. So this is a bit of the heart of our custom project. This is a forecast result of our model. So we took the training model that we just showed you and asked him to tell us how many units will be sold for 4 weeks after the end of our training test. That would then compare roughly to the month of March 2020. Because we had the data from March 2020, because we cut our data a bit earlier, we had the information of what was sold. So we decided to use that to make a comparison between what we predicted and what actually happened. As we can see here, the red dots are what the model predicted and the bars are what actually happened. Overall, we are pretty happy with the performances of the model. We are a bit over or under for some categories, but generally pretty happy with what went down. Also, as we said before, this is March 2020 data. It was locked down, so we were expecting a bit some odd patterns. But yeah, that looks like a simple graph. It was actually a lot of work. And now Ivan will walk you through what we call the inventory rebalancing strategy.
Thank you, Emma. Pretty solid results, huh? So let's elaborate on our inventory rebalancing strategy based on the results of our model. It has 2 main objectives: freeing up warehouse space by removing low-demand items and prioritizing high-demand products to ensure better stock availability and efficient resource allocation. This strategy ensures that the warehouse operates efficiently, aligning inventory levels with customer demand to reduce both overstock and shortages. So our rebalancing mechanism is built with 3 thresholds: a threshold for non-peak items, a threshold for peak items, and a dynamic threshold. We implemented these by applying a stricter threshold of 50% of average demand to low-demand products, enabling quicker rebalancing and freeing up space. A threshold of 100% is used for high-demand products to ensure we maintain sufficient stock for top-performing items. And we calculate rolling demand over 4 weeks to adjust stock in near real time, allowing dynamic response to changing demand patterns. And to monitor the effectiveness of our rebalancing strategy, we created this dashboard. And let me show you how it helps in inventory management. So like for example, for swimming wear tops, the dashboard shows no stock increase is needed for the first 3 weeks. So basically the first 3 dots are red, but sales are expected to rise in the final week, the beige dot you see in the chart. This allows proactive restocking. And for mocassins, they are flagged across all 4 weeks, indicating constantly low performance. This signals a need for reevaluation of their stock levels or potential removal. By identifying these trends weekly, the dashboard supports targeted decisions, ensuring space is used efficiently and demand is met effectively. And now back to Emma.
Thank you, Ivan. So we're going to dive a little bit into the key aspect of our project, which will be the seasonal demand sensitivity, the space optimization, and finally, we will go through some refinement and future enhancement. First off, we of course notice the importance of having a good estimate of the seasonal demand and the sensitivity of this seasonal demand. The peak season flag, which we're creating, was very useful for that. It allows the model to effectively capture demand fluctuation and ensure that the model is responding dynamically to both the peak and off-peak season for each category of item. Then we looked, of course, what was very important for us was the whole idea of space optimization. And by using the forecast generated by the model, we can focus on removing low demand item or out of season item to free up valuable warehouse space, which in return allows the company to prioritize high demand products or introducing new items. By adopting this approach, H&M can align inventory practices with long-term stock management goals like efficiency and profitability. Finally, coming down to like the enhancement and the refinement of the model, of course, we would like to make some further inquiries and acquisition in the idea of the peak season thresholds to enhance the model sensitivity to the demand fluctuation. And also, we would like to integrate economic and promotional data, looking at other external customer behavior and external influences on customer behaviors. So yeah, that was the main idea of the project. And now we have some bonus material with Ivan.
Yes, thank you, Emma. Yes, we have indeed some bonus material. Like another area for improvement in the next steps is the model training for single articles. Like towards the end of our project, we began implementing this approach and achieved pretty promising results. So we took the category of black trousers and predicted for single articles. And the model training was very, very good. So as you can see, this is our validation curve, and we almost predicted, it predicted pretty accurate. But when we went to forecasts, they were pretty much off. So as you can see, like the first item was predicted with 544 sold units for the next 30 days. And the actual sales, they were like 4 times higher. So this would be another step which we can look at in the future, and this would also make more accurate predictions, and the dashboard for inventory rebalancing would be much more accurate. And yes, this is what we would like to do in the future if we continue with this work. And now we reach the end of our presentation. Thank you so much for your attention. Feel free to ask any questions later during the breakout sessions, and also feel free to explore our work further by visiting our GitHub repository. Thanks to our cohort for the amazing 3 months. Thanks to our coaches for everything, and thanks for friends and family to attending this presentation. See you soon in the breakout rooms.